Hello, I will be recording for my project on Biosphere 504, looking at Euclideus, and we'll go from there. So I'll be sharing my screen. Okay. Okay. I will be doing a recitation presentation for Biosphere 504, and I'll be looking at Postberg's macromolecule organic compounds at the depths of Euclideus, and that's a 2018 article. Again, this is just a revisit of the article that I'll be doing a recitation for. All right, let's talk about Euclideus real quick. Euclideus is going to be one of the moons of Saturn, and it's a really dynamic, it's a dynamic satellite when you really think about it, in terms of our search for life and our exploration of space, in particular in our solar system. Euclideus is really the top candidate for life outside of planet Earth. There are several reasons why, and we'll get to that in the recitation itself. But just looking at this moon and at the satellite, it is roughly about 310 miles in terms of the size. It is the sixth largest moon of Saturn, and it is going to be one of its 150 moons. So there's 150 plus moons and satellites around Saturn itself. So it's one of the more prominent ones, and it's the one that has some cool stuff going on it. In particular, there is going to be geysers at the southern pole of Euclideus that are spewing out water and other organic materials. And that's basically what this paper is about, just the discovery of these macromolecules that are existing as part of the active regions in the southern pole of Euclideus. So just a little bit more about that. There is some clear evidence of hydrothermal vents, and also volcanic plumes that we're going to see in the ice-covered Euclideus. There's also evidence of oceans. So we have, again, when we're thinking about volcanism on Euclideus, there's evidence of that. There's evidence of oceans, and these oceans, again, are going to also have a saline content. And in addition to that, there's going to also be chemicals that are very similar to organic chemicals found on planet Earth. This is exciting. This is really cool for scientists who are planetary scientists and are studying the ideas of extraterrestrial life or life outside of planet Earth. Because really it's like the same ingredients that are proposed to have happened on Earth itself when it comes down to primitive life. So this is really cool. And a little bit more about Euclideus. It has an ice shell, roughly about 21 to 26 kilometers thick. We're also going to be looking at its global oceans. So again, it has a presence of an ocean on Euclideus, which is pretty rad. It has a rocky core, and so we can see its density as follows. There are evidence of hydrothermal vents, especially in the southern pole region. And we're going to be talking about the probe that actually went and collected some of the dust from those hydrothermal vents and did a bit of analysis on it. It also has this really cool thing called tiger stripes. These are, again, going to be looking at jets as they relate to these plumes that are being sent out into space. And again, part of the planet itself, like what was mentioned, is the plumes themselves, and these are going to consist of grains. These grains are icy grains, along with dust grains that are going to be emitted from not the planet, but the moon itself. Going a little bit more about moons. So Saturn is quite a beautiful and dynamic planet. We can see that there are over 150 moons. and satellites that are going to be in its orbits. As we know, Saturn has its rings, and several of the moons itself are actually ways to corral the rings. So that's a pretty cool thing when you think about Saturn is the rings, as we know, are made out of dust and ice particles. The moons themselves actually hold in several of the rings around Saturn. So that's probably where we are going to, of course, find Cladius is in one of the rings of Saturn, in particular the E ring. So Saturn, it has several different rings, and Cladius is going to be actually creating a ring around Saturn. So the plume of dust and ice that is emitted from the geysers and the volcanism that is happening specifically in the southern pole of Cladius is actually spraying ice into space, hot fire. So these chunks are going to go into orbit around Saturn and create its E-ring. Then again, when we're looking at Saturn and its rings, just going a little ahead before going back, we are going to see that there's our A ring, our B ring, C, D, and all of that rings, right? And all the way up to our G ring. We're going to see that these rings are going to be according to the content that is going to be floating around Saturn itself. And we're able to utilize science in order to analyze what that content actually is. In particular, with this particular paper, they use mass spectrometers. So essentially, they took a sample through Cassini and they ionized it. They basically utilize a spectrometer to see the mass of the content in the ice and the dust particles, and was able to see like the again content of what the mass of the particular elements were. So just a little bit more about the ways that they measured this data. They used two different measurement methods. One is the CDA and the other one is called INMS. And these are two forms of mass spectrometers, again, looking at the mass of the elements and analyzing the mass of the elements and using a comparative model in order to be able to ascertain what particular elements are in the sample. So they use the CDA, the Cosmic Dust Analyzer, and then the ion neutral mass spectrometer. And as you can see in Cassini over here, you can see all of the doodads and so forth that are a part of this probe into space. And just doing a little background reading about this mission, it was launched in roughly about 2005. And it wasn't necessarily to go to Enceladus. It was just while it was in the neighborhood, you could say, it saw some really neat happenings at the southern pole of Enceladus and went and actually collected samples. So that's what we'll be looking at in today's kind of recitation. Macromolecules are what they found. And when we're thinking about life itself, life is life depends on life. When we examine life, we can see that the little is a microcosm to the macrocosm, and that everything is really, it's all connected. And so when we're looking at the microcosm, we can see a mirror to the macrocosm as well. In particular, we're going to be looking at macromolecules and the formation of macromolecules as a part of the genesis of life itself, not just on planet Earth, but kind of like the same ingredients that, again, different cooks, different plates, right? So you can have the same ingredients, but it's all about how the cook puts it together. And in particular, would be like the dynamics, the physical dynamics of the planet or the satellites that creates the souffle of creation. So there's going to be some common denominators that we're going to be looking at when it comes down to exogenous sources and endogenous sources. Exogenous sources, of course, are going to be from like outside of the planet or the satellite. and that could be anywhere from asteroids, interstellar dust, comets. This is where life is coming into the satellite or the planet. Again, it can be seen in the well-known theory of panspermia. Is the idea of that life, it didn't necessarily exist in one place, but is actually a continuation or a tree or a branch of a much larger organism, as you could say. And then there's the endogenous sources. Endogenous sources are, again, kind of like looking at Miller synthesis, the synthesis of urea, um, volcanic activity, hydrothermal resources. A lot of thought has also gone into like nuclear geysers. So the heating up of nuclear material through either through just processes that happen naturally inside of the core of the earth, or just like yeah, those geysers that have those nuclear components to them or nuclear elements inside of them. So those are kind of those endogenous sources, those things that exist on the satellite or the planet, and then the exogenous sources. And many scientists believe like it's a combination of the two, right? It's not just one or the other, but most likely both. Kind of like the idea of like the Earth or the planet had to be ready for the exogenous sources to flourish, right? So there's that too. When we're looking at the macromolecules in this paper, we're going to be looking at several specific ones, and they're going to be, in particular, hydrocarbons, and eventually looking at how we can take things such as monomers and turn them into more robust and more complex uh, even organisms. So a really cool thing to think about is the role of thermodynamics, the role of heat, the role of energy in the transformation of, we would say, non-living or abiotic species to biotic species, right? So like the transformation between biotic and abiotic would entirely involve energy, right? And this transition between, I love how it's described as thermodynamic hurricane, right? This entropy versus entropy, and the balancing act between the two in the formation of structure, or kind of the more primitive structure, or more chaos, as we would say. Polymerization is going to be something that this article also talks a little bit about the idea of going from a monomer. And this is a cute little graph. Show the kiddos on looking at carbohydrates, proteins, lipids, and nucleic acids, and how we have a monomer, kind of like the building block of a higher form, right? So we have our monosaccharides that go into making our polysaccharides, our amino acids that go into making our polypeptides, fatty acids that make larger fats and lipids, and then nucleotides that go into creation of things such as DNA, RNA, and ATP synthesis. Why does this matter? Well, because there's evidence of some of the very same materials that are building blocks for life on planet Earth found somewhere else. And that matters because it's exciting. That matters because it is evidence that we are part of something bigger. And so in this article, data was analyzed, and it indicated in particular that on the oceans of the Celsius, that there was actually a biofilm. And this biofilm could be a precursor to life and processes on planet Earth. And I totally spelled that wrong, and I own that. This is a credit from Dr. Bruce Damer. He did an excellent lecture on this idea of hot springs, the idea of this thermal dynamic that needed to be added in order to create life itself. He started off basically in this idea of synthesis, is that life in itself is not of the earth, but is only nourished or natured by earth. that life exists outside of Earth, and its synthesis is the same thing as when we're looking at all of the other chemicals. If we're looking at the birth of stars or the death of stars, right? In particular, we would see some of these biochemicals or this chemistry of life emerging from fusion inside of the cores of stars to actually the synthesis of biomolecules. So the first step is synthesis, and that's going to happen not necessarily on the Earth, but as part of a larger life system outside of the Earth. Then over time, it's this step of accumulation, this idea of like as chemicals are added to the Earth, as conditions are made right, things start to change, right? It's like a good soup, right? You put in the soup, you put in your chemicals, or you put your ingredients, your carrots, your potatoes, all that yummy stuff into the soup. And then as you're putting more heat on the flame, things start to change, right? As energy is added, as a thermal component is added, we're going to see in areas, density is going to increase in colder areas where things are going to become less dense when we add a thermal component to it. This is also going to be related to cooling patterns, right? As we know, with the Milankovitch cycles on our planet, right? We go through different orbits and different frequencies in terms of our axial tilt. So we can see that there will be different conditions that have happened in Earth's past that may not be necessarily happening today. And that creates some of this accumulation and concentration of some of these proto-life. As concentration happens, we go into a refinement stage, which we would be calling kind of like the cycling stage. Again, it's like an iteration. If you're into fractals or anything like that, it's like one iteration leads to the next iteration, it leads to the next iteration. And as these iterations are happening, complexities evolve, right? And so the increase in complexity is also going to be part of the iteration process itself. So we can see that there will be a cycling that will eventually create a more adaptive organism versus a least adaptive organism, where that more adaptive organism is reproducing at higher rates than the least adaptive and therefore passing on its genes eventually when it comes down to not proto-life, but actually diverse and more complex life. Distribution is going to be happening, and then we're going to be looking at that idea of adaptation, right? What is around is what made it, essentially, right? Not necessarily what is the perfect, but yeah, what is just good enough for the situation at the time. Then that leads to colonization, right? And so that's going to lead to the formation of life itself. And in the image, he uses stromatolites. You can see kind of like the stromatolites and this idea of like cyanobacteria and of how whatever we call life is entirely connected to the environment. So in our reading, we were looking at Enceladus, and we were looking at how some of the features, the physical features of Enceladus, are very exciting for the formation of organic molecules and the formation of life itself. Again, evidence of this film that is existing on the ocean surface gives credence to the idea of the primitive forms of life existing on Enceladus. This is again just looking at the hydrothermal vents and looking at the grains. So kind of thinking about the grains that are going to be produced as parts of the a part of the emissions from this particular unit. So we're going to be looking at water. We can see that water was present. We can also see that salt was present. Non-volatile organics and volatile organics were present. This is super exciting. Again, it's just more evidence that is confirming that chemistry leads to more complex and more, could say, life itself. So again, when we're looking at how all of this was, the methodology behind collecting all of this data, half of the article, if not the majority of the article, was all about methods, which I love. It's important to see how things are done. Basically, it took a various sample of the ice and compared the species of what was present and used, again, mass to be able to see what particular species was going to be in abundance. And finding some of the compounds, organic compounds, was one of the things that, again, this article really hit home with. So again, when we're looking at the origins of life on planet Earth, or origins of life in general, we can see that there's going to be those exogenous and endogenous sources. Earth is a fantastic, beautiful, and amazing planet, and is truly remarkable in terms of the formation of intelligent life and diversity of life. However, life in itself may not have existed on our planet, and there's a lot of evidence that suggests that the conditions on our planet evolved life to the way it is now, but that life and potentially intelligent, vastly more intelligent life exists in other places. And there's just a lot of evidence to support that. So again, when we're looking at origins of life on planet Earth, we would think about things such as panspermia, hydrothermal vents, nuclear geysers, right? Having that physical component in terms of the readiness of a planet or a satellite, and then having that exogenous source meeting that endogenic source, very much like a garden, right? A garden of planets. Wrapping up real quick with hydrothermal vents, and then do you have some questions for the class? There's just a lot of evidence that life has evolved from chemistry and the mixture of chemistry and energy, or the mixture of this thermal component. Whatever you call energy, people call energy God or goddess, right? People call energy physical component of, thermal interactions. There's many of ways that we could call energy, but energy is real. And we can see that energy is the driving force behind all of creation. So one of the really amazing things are that on planet Earth, the majority of our energy when we think about life comes from our lovely star, our sun. But there is life that also exists inside of hydrothermal vents that are devoid of any photosynthetic processes or devoid of any solar photons. And this again gives credence to Enceladus being a planet that could host maybe life similar to life that exists in these regions on our own planet. So again, biosignatures of microbial life exist in fragments of polymers and specialized hydrocarbons. We can also examine them in polycystic atomic hydrocarbons. So these are things that were observed as part of the analysis of Enceladus. And I included like a little quote or blurb from the actual analysis, because I thought it was really cool to compare how the CDA and the INMS looked at the different species and really categorized them based on their mass units. And we're able to see that there was a correlation. So like that, the reading from the CDA and the INMS were similar. They got the same data, though they were different machines. And basically in the image, looks like it didn't load up, my bad. They basically had abundance at 31 and different peaks. And these peaks were representing products, breakup products. So when they were going through the spectrometer, we could see that the products are going to be reduced in size. and also are going to be illustrative of some of organic molecules, right? So in particular, there was peaks at peak 30 and 31 that were indicative of specific organic molecules themselves. Here goes some of the data also that as you would have read the article, you would have analyzed in terms of the figures. And so wrapping this up, I have a couple questions. So what evidence did this reading affirm about Enceladus, about being hospitable life? You can pause right here if this is being shown in class and discuss and give like that fun wait time thing that all us teachers love. Okay, jazz hands. Hopefully the wait time is over. Let's look at the next role or the next letter. What role do you think endogenous, like such as hydrothermal vents versus exogenous, such as interstellar dust, might have on the potential for life on Enceladus? And totally spelled wrong twice. So yes, I get a big hug there. Um, what role do you think that endogenous or exogenous forces have on life itself or the potential of life? You can pause here as well. Jazz hands again. Hopefully that was a cool discussion. And the last question is the presence of water, salts, and hydrocarbon when we're looking at the data in the INMS and the CDA were analyzed. Given our previous readings, what elements would further justify life on Enceladus? So what other elements would a planetary scientist look for in terms of additional support for life on Enceladus? Hey, jazz hands all the way. Thank you for listening to my recitation. And I hope all of you have a great and amazing day. I will catch you on the flip side. Take care. Bye, everyone.